Howdy, everybody. Hope you're doing well wherever you are and things are going okay. I just want to start by saying thank you again. As always, I appreciate the community interaction in the comments. It's really great to be able to uh, to answer questions. I love doing that and to teach these things, to talk about them. Because they help me and hopefully they're helping you too. So that's why I'm doing these videos, to try and build a community where we can all grow and learn together. And hopefully this video will be no different. What the plan is, just at a high level, is I want to talk a little bit about asynchronous programming, and specifically within the Rust ecosystem and using Tokio. So that was a lot of very drilling down into what we're going to be talking about. And I do say that because there's a lot of different types of asynchronous programming, or different ways to do asynchronous programming, I guess, is maybe the way to say it. Rust has a very specific way of doing it, and it's not the same as you might do it in JavaScript or another language. But they all kind of have similar patterns, and they even have similar patterns to things like Go routines in Go, right? And so we'll try and discuss them and kind of weed out the things that I know about the languages and these runtimes that do concurrent or asynchronous programming, how they work and what they do, and in particular how they differ from what we solved last video. If you remember, we used system threads or OS threads, and channels to communicate. We'll still use channels, but we used our own threads, and that comes with its own set of pros and cons too, right? So, that's the goal, is just to kind of discuss those and then look at the code and see how it's changed from, the threaded model to the asynchronous model, and how that can help you or how it can't. So, given that though, let's just get into it. And I'm going to hide this one for a little bit for a second. We're not quite ready to talk about it. But if you remember our previous solution, basically, maybe I should just talk about how the day worked, right? As remember, we had a bunch of amplifiers and we wanted to chain inputs, right? So amplifier 1 would do some work for our int code computer, and then it would send its output to amplifier 2. And then amplifier 2 would do some work, and it would, that didn't work at all. Am I doing this wrong? I want a line. There you go. Anyway, I'm spending too much time worrying about the lines. But the idea is you'd kind of change the chain the output of one as the input of the other. And for part 2, it became a feedback loop where amplifier 5, I only have 3 here, but would wrap back around and send its output to amplifier 1. And you go in this continuous loop, right? And you could do it in a round robin approach where you basically just run each process until it stops. But I thought it would be a good way to show how threads and channels work, because they're a great way for you to reason about multiple processes doing their own thing and then communicating when they need to. And so that's how it worked. And I did create, I don't know if I mentioned this, but I used system threads or OS threads, or sometimes what they're called. But the idea is they're a thread that's managed by your operating system. I use Linux, so I'm going to use a bunch of Linux terminology, but they do translate to Mac OS and, BSD and Windows. They may just have different nomenclature, but they're largely work the same, right? The idea behind an OS thread, though, is the OS manages it. You tell it the code you want it to run, and it will run it, and it will decide when to stop running it and give something else priority. So you don't really have much say in that. But you're kind of guaranteed to be able to run your stuff in that thread and not have to worry about too much, right? Unless your system's totally hanging and using all the stuff, your stuff is going to run. It's going to be very efficient at running that stuff. But there is a bit of overhead in setting up a thread and using a thread. And so it while it definitely solves our problem, there are some cases where it may not be a great solution. So in our case, I think I had just a thread per amplifier and then a couple threads to help with the channel communication stuff. So maybe a dozen in total. That's not bad, right? But you could imagine a case where you might need thousands or hundreds of thousands or millions of threads, meaning you're wanting to do a lot of things concurrently. Like think, for example, of a, I don't know, some kind of TCP system like an old IRC channel. I don't know if you're familiar with IRC, but it's like a text channel communication thing where you can like talk to people. It's old man's Discord is maybe the way to think about it. And I don't want to say, I don't say that jokingly because I did use it back when I was young and in the early days. So I think IRC is still cool and useful. But you can imagine like you may have thousands or tens of thousands or hundreds of thousands of concurrently connected computers to your system, right? Maybe you're super popular, your IRC server is, and so you want to be able to handle all those connections at the same time. Well, that can get really hard spinning up all of these threads, right? In fact, your system, I can probably do it. You can see my system says it only allows 1 million threads. So the thread max count is 1 million, which is not a ton, but or it is a ton, I should say. It is a ton. You'd probably never reach that. But this is pretty heavyweight, right? And what often ends up happening is the effort of spinning up the thread versus the cost of like processing the user, handling the user's input is like not worth it. And why do I say that? When you're doing a networked application, a lot of the time is spent waiting to receive some input or waiting for it to be able to send some output, right? Think about all of our processes when we were stepping through it. Maybe I can just show you again, right? Is like, as we're stepping through our processes, eventually we get to a point where we want to receive a new input, right? So you can see this one is now waiting. This first thread is now waiting for input. But there's no input to give, so it has nothing to do. What happens on the background now is that thread is not doing anything. It's just sitting there not doing anything, right? And it won't do anything until, right, we go through the other threads. They're all, you can see like, especially in this case, once we get all the stuff done, all of the channels are empty. So we literally have every single thread that's waiting for some work to do, except for this one, because it happens to have something on its channel to process. So we can do that work, send the results to the other channel. You can see over here, it sent it to the other one, but now it's waiting again, right? So the way to think about this is we have 5 threads running, but only one of them is actually active at a time. And so it's not an efficient use of resources. And again, this is not a big deal. We only have 5 processes. But you can imagine on some really important big systems, you may have hundreds of thousands or millions of connections that you want to process, but only a handful of them may be ready at any given time. And I just want to tell you a little bit about how we did it so you maybe understand the history of where this all came about. So one thing that happened, at least this is how I learned through this stuff, is the Linux came out with an epoll function. And essentially what it does is it allows you to poll for multiple open handles, and it will tell you which ones are ready to receive data, right? So when this was introduced, when was it first introduced? 2004, right? It was really cool. The idea that, we can now, instead of having like a thread per TCP socket, again, let's pretend it's I think I may have some code some examples for this. Like here's our socket, right? Is normally the socket would look something like this, is where we have some loop that we're going to run forever. And we get the next message off the stream. That's going to wait until the user actually sends a message. And they're not typing furiously every second, right? They maybe send a message and then they're reading. They're not really doing anything. And they're not dealing with anything on that socket, that message, until they actually type something and send it, right? And then maybe you do some work to validate it, and then maybe you send that message off to some other system that's going to like propagate it to the other users or whatever, right? But again, this loop is often blocking on this thing, right? So what epoll allowed you to do, or still allows you to do, is to basically say, hey, I want to wait on all of these events, and I want you, and it will kind of sit there and wait until one or more events are ready, and then it will send you the number of events that are ready to process, and then you can process it, right? So the way you would do it, let me go back to my diagram, is you'd have, let's move these over here. You have these three different programs. They're called amplifiers, but let's just, like, this is user 1, and this is user 2. And this is user 3. What you do is you'd have one thread that kind of has your epoll, and then you'd have these, you'd have a thread pool is what you do, is you'd make a thread pool. And so we'll just use these two. But the idea is this thread would do the epoll, and it would say, oh, user 1 and user 3 are ready to receive data, right? Their call to this this message is ready for you to process. And then what you would do is you would stack those things in your thread pool, right? And wait, I don't know why that went to the back all of a sudden. Order. Bring to front. Okay, so you'd put user 1 on here, and you'd put user 3 on here, and it would do the processing, and then the epoll, this one would be done, the epoll, and this one's still working, but the epoll in its own thread would eventually say, oh, user 2 is ready, and then it would put it, and then you'd put it on the thread pool to do that. And maybe user 1's still doing its stuff, right? And so it's still waiting, but user 2 and 3 can utilize these threads in the thread pool to do their work, right? And this is more efficient because you aren't like creating and destroying threads. You're maintaining a thread. These threads, you're keeping them running, and you're just using epoll to tell you when events are ready with these tasks or these functions, these streams, and as they are, they can be put on a thread pool, in a thread pool to do their work. And we all did this in C, or at least I did. I can't say we all did it. We all did this in C, and it was actually really cool, right? It was a different model, and if you've ever heard of Apache or Nginx, they kind of worked in different ways, right? Apache was, I'm going to spawn a new process and I'm going to like farm work off to those processes. Nginx used this kind of epoll thing. I think it probably used epoll. It used something similar where it would say, hey, things are ready. I'm going to process the things that are ready. And what that allowed you to do is in fewer threads, get more work done. And suddenly, where Apache maybe would have a limit of 10,000 or whatever concurrent requests, you had to like set these values in Apache at the time. You may not need to do this now, but you had to set these values where you had some limit at the time, because Apache would just like gobble up all the system resources and not use them super efficiently. Apache had its own strengths too, right? I don't want to just belittle Apache for what it did, but what Nginx brought was, hey, look, you can now do hundreds of thousands of concurrent connections, no problem, because the reality is only a few of them are going to be like ready to use at a given time. Some very small subset are going to be like ready to use at a given time, and you can just put those in your thread pool, let them process, and slowly add events to your thread pool as the things are happening. And you make this cool loop and get all these things done. It felt really cool to do it, right? Well, modern languages came around and said, we can do that too. And that's where you get something like Go, right? Go works very similar. When you spawn a Go routine, it will put that work to do. The runtime will recognize that that's some chunk of code that needs to be processed, and it will kind of schedule it, is the way to think about it, in one of the threads that it's managing, right? And whenever you do an event that requires like IO, it will say like, oh, okay, you're going to block. I'm going to put something else to process there, right? And it will do that work, kind of the stuff we talked about right here. The runtime manages that, right? And the same, you can do the same thing in Rust, but you use asynchronous programming and something like Tokio, which we'll talk about a little bit, right? And the difference with asynchronous programming and something like Go, I should say that Go essentially does asynchronous programming. It just does it under the hood. The idea behind asynchronous programming is you tell the system, the runtime, when you're going to make a call that could block. And you do that by calling await. You say this thing could potentially block, so I'm going to await on it. And then you just make sure you tag all your functions that you're using await in as async, meaning it's an asynchronous function, so that the system knows that, oh, this thing could block, and if it blocks, I should notify the runtime that maybe there's something more interesting or more that you could be doing with your resources while this thing is blocked, right? And that's a really high level description. And I'm sure I glossed over some stuff, but that's generally how asynchronous programming works. And you can see some examples in here in the Hello Tokyo. Well, we'll actually look at an example, but notice they're using the async function here to say, hey, this is an asynchronous function, meaning at some points it could block, and we'll want to notify the runtime that block could happen, so that it can manage when those things are ready or when to like context switch to something else while it's waiting. And then we use these await commands to say, hey, this function has to do something that could block, and so you can like wait on this. And essentially what it does is it removes the blocking from the system, because anytime you would block, it can pause that thing while it's waiting for whatever it's waiting for and do some other work, right? I should just clarify too that what something like this connect function actually returns is a future. And what you're saying is, I want to await on that future finishing. So in JavaScript, they call them promises. They have differences, but generally the idea is when you await on a future, you're saying, I'm going to wait until that thing finishes, right? You can do other things like select, which I'll show you in a second, right? But how does that work? How does that change our code, right? So if we look at what this function was doing, where we get a message that could block, then we validate the message, say it has to make some database calls to make sure the message meets certain requirements or hasn't gone over a limit or whatever, I don't know, something like that. That could block us too. And then when we want to send the message, to some system that's going to propagate it or whatever, that could block as well, right? So all of these are like blocking messages. How do we make that an asynchronous call? Well, we add the async tag to our async property. I don't know what they call this actually. Should we look it up right now? I think I don't know, just declares the function. Someone in the comments tell me it's just a keyword, but it is telling the compiler that, and the Tokio runtime, that this is happening asynchronously, and so you can do your fun stuff in it, right? And then anytime we do something that could potentially block, we just call the await function, right? So this get next message is going to do something on the stream. Presumably it's going to try and read from the stream, for example, and that read might block if there's no message to be read, or the network is saturated, and so it's not getting anything from this user at this point, right? So you call await here, and that's a signal to Tokio, hey, this part of the code could block, and if it does, then you can like kind of pause where we're at right here, and go handle other stuff. until this is ready, and then you can come back to me, right? And then you do the same thing here for validate message, for example. You say, oh, I'm going to await. And then when you send it on the queue, you say, I'm going to await as well. These are all cues to, again, Tokio or the asynchronous runtime that you want to block, right? Or that these may not be ready. And if they aren't, pause what you're doing right here and go do it somewhere else, right? And then how do we actually run this, right? So here's an example of how it might look. Is now we created an asynchronous main function, and we call Tokio. We use the Tokio main label right here to kind of like turn it into a Tokio runtime, or to like start up the Tokio runtime, and wrap this function in that stuff, right? In that runtime. And so how does this code look? Well, now we call, we bind to our listener, and then, we create our little channel for our sender that we're going to use for the handle. And then we just listen for incoming connections, right? And as we get connections, we call Tokio spawn, this part right here, right? And we're saying, hey, I want to spawn a new task to handle this user stream. And you just call the code that you normally call, right? So the actual call doesn't look much different. We still call handle user stream, but we wrap it in this Tokio spawn. And this is saying, hey, Tokio, I have a task for you to run that has asynchronous code in it. Will you add that to your list of tasks and do that processing? And under the hood, what's happening is Tokio is essentially doing what we all did with this epoll back in the day when we were all young and didn't have beards or didn't have gray beards. But I want to, again, just reiterate a little bit how it looks, right? And so you have this Tokio runtime, and it's piled up a bunch of threads. Again, this is very specific to Tokio and Rust, but Tokio in specific. Like, for example, Node.js, at least the last time I used it, only does one thread. And so the asynchronous programming is like happening on a single thread. Tokio will spawn multiple threads for you and like run multiple of these things at the same time, right? So, but you can imagine as a user connects and it's sending messages, it may put it on this thread, and then another user connects and it puts it on this thread, and then another user connects and it's working on this thread. And then what will happen is, another user is connecting, and we'll put this in the Tokio task queue, right, to do. So Tokio is waiting to do something with it, but it knows there's no room yet. Eventually, one of these will like await, right? So if we go back up here, when we call get message, this user will have sent his message and call await, and this will pop off the queue, and then Tokio can say, oh, I have room for something. I'm going to put this guy back on, right? And how it chooses to use these are kind of an implementation detail you don't need to worry about. Like, imagine user 1 and user 4 are both ready to do some work, and there's only this thread available. How it picks that, kind of depends on. I looked a little bit, and it looks like they have like a little metric system where they say like, how much work has been done on this one versus this one, kind of like prioritize it and stuff like that. But you don't really have to worry about that. The idea is Tokio will make sure that, everyone is getting some opportunity to do stuff on there. With the one gotcha that let's suppose we haven't written our code very well and we aren't ever awaiting, right? We're just doing a bunch of expensive computations forever and ever. It will block this thread, right? User 1 will never go away. And then that thread will kind of be down, and you'll kind of, it'll have to share the work between these other two threads that are happening, right? But again, why is this helpful, and why is this potentially better over using threads is you could notice here is you just kind of fire and forget in the code, right? You say, hey, Tokio, handle this user stream, and you just kind of throw it over the wall and let it do its thing. And much like in Go, you can have hundreds of thousands of these tasks running concurrently, wanting to do some work, reading and sending and doing that stuff. And Tokio or Go, they'll handle it just fine, right? They're basically just, what's the list of things that are ready to do? What are the resources I have available to put it on there to do that work? And then as you await, you can do things. And again, just one gotcha with this is, and they talk about in their Tokio stuff, is right here, like when not to use Tokio. It mentions if you have like heavy CPU bound computations, Tokio will not help you, right? It's mostly meant for IO bound applications. And so if you're using Tokio that has some CPU bound computation, that's fine, obviously. But again, if you have some kind of process like this user one that's going to be sitting here for like 5 minutes on this thread or 5 seconds, whatever, and you have multiple of those, they can start to exhaust the thread that you have available, right? And so that's where you might want to start thinking about utilizing multiple like concurrent programming paradigms, right? So, for example, I think I'd mentioned this when I was talking in the comments, is like, imagine you have like a GUI, a front end, and it needs to render, you know, to keep its FPS high for like a game, for example. You don't want that render to ever block, right? And so you may want to run that in its own thread over here, right? So maybe you have, and this is the cool thing about Rust and Tokio, is you can do that, right? Is you can say, hey, I'm going to have my GUI thread, right? That's doing my game data. And it's always going to have, well, I guess it's just thread here. And we're going to have the GUI right here. And so you have this thread on the side that's doing its own thing. It's a system thread. And so it's using like the system OS thread system to the OS to like make it to process the GUI. And it's not going to randomly get taken away by Tokio, right? Now, the gotcha is you can't easily run asynchronous code in here, so you have to do a separation, right? And I'll show you in the code how I kind of did that a little bit. But the idea is when you want to render a frame, you want to render a frame, right? You don't want to wait for some call that may block or may not be ready in the runtime, right? So you can have all your other work going down in here, and then you can have your main thread working on the GUI that's just never blocking and, never stopping. So that's where the Tokio runtime, I think, is really cool, and Rust is really cool, because you can't actually do this in Go, right? In Go, if you have like the Go runtime, everything runs in a Go routine. Everything kind of runs in a Go routine. And you can't tell some Go routine, hey, I want to have priority. At least that I know of. I don't think you can. And so what you'd normally do is you'd actually say, well, if I have some front end GUI that needs to be well performant and some back end that I need to do some stuff on, you'll often do it in two separate programs and then just have them communicate over, you know, a local socket or something like that, where, or some other thing like that. You can use shared memory, things like that, right? But the idea is you'd have a single thread over here, or a single program over here that's never going to be preempted because it's not running anything else, and then you have the runtime over here. Now, I will say for most cases that doesn't matter, like, and there's definitely ways to get around this, right? Even in Go. But it does. I like it that Tokio does give you the ability to do this. Have I said the gotcha though, right? If you do any blocking calls here, again, it's going to take over that thread. And so that's where you just have to be careful as a programmer, right? So you need to know, hey, am I going to make some blocking network call, right? There's nothing stopping you from using this handle user socket in an async manner, right? You can spawn that handle user, even though it doesn't await, and then it will start blocking, and Tokio, once it starts running that, may not ever have an opportunity to await or to preempt it, and it will like basically take over that thread forever, right? So again, that's just something to watch out for. We're doing a bit of a toy program for our int code, and so it's not a huge deal, but it's just something to think about. If you start doing this stuff in the real world, you need to be thinking about, hey, am I giving Tokio enough places where it can preempt my code to do that stuff. And obviously, if you're doing network programming like we're kind of doing between these processes, there will be lots of opportunities, presumably, especially while you're running. There'll be lots of times where your thing is stalled waiting on input or stalled waiting to output something. And that's when Tokio really shines, is it can figure out when to do things and what things are not ready, and putting them in threads that are already up and running and able to process, right? So this is kind of the modern way of the way these things work. And again, I will say it's kind of different for every language. There's pros and cons to doing it with Tokio and Async. There's pros and cons of using the Go runtime. Like, for example, if you're using Go, you don't see a wait or async in your code, right? And that's because Go is doing it under the hood for you. When you call a read on a socket, if it's not ready, the Go knows that it's not ready, and it won't, try and it won't like block on that thread, right? So in that sense, or block within that Go routine that's processing, I should say, right? So you have to be more explicit here in Rust and Tokio, but it does allow you to often, because of that, you can like specify where you want to run the runtime, or if you want to at all, right? That's the nice thing about Rust, is you can say, oh, I don't need an asynchronous runtime for my, my command line application or whatever. I'm just not going to include it at all. But anyway, I want to show you how it works. So let's just kind of go look at the code and see what happens. So here, if we go back to the code, what changed from the previous thing? Oh, well, I should say one of the things that changed is, because we're kind of working on the same code, I thought it would be good to just kind of keep it in a repo. So here's the repo. I'll put a link in the description, but this should have all the up-to-date code. Feel free to fork it and make your own changes, do pull requests, whatever. This will be a great way for you to kind of like show me what you're doing, either via issues or pull requests. You can use this to help communicate with me about what's going on. And what you're doing with your int code computer. I'd love to see it again, right? So send me an issue or a pull request so I can look at your code. Love to see it. Or if you've found something to improve or code to improve, I'd love to see it as well, and I'll incorporate it, and we could talk about it in future videos. So there it is. But what changes in the code? Well, again, when you're doing asynchronous programming, really all that changes is you need to tag which ones are asynchronous, which functions are asynchronous, and you need to notify, you need to await on any of those like futures, right? Those things that could happen in the future, those things that could block, that Tokio will need to know about so it can, it can do its stuff, right? So you can see a lot of these get instructions and stuff doesn't change. I did modify the communication, the channel a little bit. I guess I can show you what that looks like. Basically, I created a channel sender and a channel receiver to work on these the queues. I should name these buffers because they're really buffers. I think I called them queue first because I was using a vec deck. So let's just change those really fast. Da, 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 da. Okay, so but they basically what I did was I wanted to see, right, in the UI, I wanted to be able to see what's in the channel, like what's in the buffer, what's not yet been sent in the channel, and so I basically created a wrapper around this buffer, and it works exactly like the channels that we talked about last time. I should say that, sorry, I just got a popcorn kernel in my mouth. I was eating a bowl of popcorn before this. Where was I? Oh, Tokio has its own channels that are asynchronous channels, and you can use either one. depending on your use case, there's pros and cons. I tried to use Tokio's channels just so you could see how they work. But you will need to use them as well as potentially your mutexes from Tokio if they're going to be used over an await command, right? So like as you await, you may need to use these. And so in this case I did because I'm going to be awaiting through these sends and receives. And so that's where I had to use this. But I didn't have to use it for the mutex. I'm sorry if this part is confusing, right? Is like Tokio, right? Its runtime is may like take your task and put it on different threads. And so you need to be able to like quote unquote send your objects from one thread to the other. And the standard library's mutex doesn't allow you to send, right? And so you'd have an issue if you're trying to send over those. In this case, I'm not. You can see like when I get a send, for example, I lock right here, but then I just send and I'm done, right? I could probably actually do this, drop the lock like this, just so it drops before we send. But the idea is because the lock isn't used at this point, I'm okay. And then the same thing with down here is you can see I only lock it at this one point, and I don't lock it anything that I would await through using it, right? Like if I were to pass this mutex lock into something that was awaiting, then I might have to use Tokio's lock. This has all been maybe too confusing, especially if you're very new to asynchronous programming. You can just ignore the previous 2 minutes. I apologize for that. But again, essentially the channel is just a way for you to get a sender and receiver, but I want to be able to see in the UI what's in the buffer, because normally you can't create like a Tokio or a standard library channel and say, hey, give me a list of all the things that are currently in the queue, right? But I wanted to be able to do that right here for, I'm making changes all over the place as we go. I wanted to be able to do that here for the UI, right? So let's go back to the process. And so what changes? Well, you can see when we call run right here, now we have to do it asynchronously because it's possible that a step could halt, right? It would need to wait for input. And you can see the step also is async because it needs to wait while it evaluates the instruction. It may need to await while it evaluates the instruction. And evaluate instruction is also async because down here, when we're calling receive for our input and send for our output operations, they will await, right? They may not finish, or they may not be ready, I should say, to receive or send. And so we need to await on those. And this is probably not a great description of it, but the way that I often describe it is your async functions will kind of poison the whole stack. Because we async the evaluate instruction, anything that calls evaluate instruction will need to be async as well, and it will need to await on evaluate instruction, right? And so you can see step itself doesn't do anything asynchronous except for evaluate instruction, but it has to await on the instruction, on the evaluate instruction, and so it needs to be async as well. Run itself, besides the step, doesn't do anything else asynchronously, but because it calls step, which calls evaluate instruction, it needs to be async as well. And in that sense, it kind of like poisons the stack. It means like anything up and above needs to be asynchronous. And I should add that this kind of makes sense because anytime you're doing asynchronous programming, if anything ever has to await, that is, if anything needs to like notify the runtime is, hey, I may block here, then anything that has called that function or that will call that function needs to do that as well, right? And it needs to happen recursively, right? So that's why I say it kind of like poisons the stack. In that sense, it makes everything asynchronous. But that's okay. That's the way that you want to do it anyway, right? Is you want to be able to have all these places where Tokio can say, oh, I need to, these are places where it'll block. Do I need to preempt at this point? Meaning like pull the task off the thread and put something else on that thread to do some processing, right? But this instruction otherwise doesn't change, right? I'm still, in fact, if you look at the previous code, it probably looked exactly the same, except I added an await here. I probably added this result, and then I added this async. A lot of the channel stuff return results that were easier to, as opposed to unwrapping them and potentially, what I noticed when you were unwrapping is you could get strange race conditions, especially in the UI. And so we just bubble up the results, and we do a lot of like matching on OKR errors, right? And we try and handle those errors. And so that's really all that changed here. But let's go to the day 7 and look at how it changed. So you can see here is now I'm using that again, that Tokio main, and what this is doing is transforming macro. Was it a declarative macro? What it's doing is transforming this function to essentially say, hey, load the Tokio runtime and then execute this code in here. I think it tells you here how it works somewhere. Yeah, right here. So this Tokio main, I can zoom in a little bit. When you add this Tokio main, it literally turns it into this. It's like a macro, right? And it says, I'm going to turn this function into this function right here. And what this is doing is building the runtime and then making your asynchronous, running your asynchronous code in that runtime, right? And so we're just doing that same thing. Again, I think we talked about this last time, is because we have two, we can run the UI or we can run the two parts. Now, again, both the parts and the UI both use asynchronous programming, so you can see we're awaiting, right? But how does like part 1 change, for example? We'll look at part 1. Part 2 is essentially the same, and then we can look at the 2e. So I broke it up to just run a single permutation where we say, hey, given the program and the permutation and a place to send the result, I want you to run this permutation and spit it out. So how does that work? Actually, let's look at part 2 because I think it's more interesting. It's doing the same thing, but we create our channels. That's not any different than before. And then we pass true where we tell it to like block on receive calls. The UI doesn't do that, but I moved that out of the processor and put it into the channel logic. So the channel itself determines whether it's going to block or not when it tries to receive. They both still await, but you call a try receive function. I guess I can go there and show you. We were just there, right? You can see in here on the receive function, we give it this block on value, and then we tell it, hey, if we are supposed to block on it, we call receive await, and what that does is it says, hey, give me something off this channel. If it's not ready, it will await, right? If we aren't blocking, which if we don't want to like block ever, and this is when we'd use it in the UI, right? For example, if you press like the step button in the UI and it goes to receive, but the receive is not ready, that could potentially block, right? And now that I think about it, you might actually be able to fix this. Because if the thread itself is not ready, it will just kind of sit, maybe I'll fix that in another iteration. But I call try receive here, which will always return immediately. Either the value's available and it will return it, or it's not ready, and that means we need to like keep process. We need to like basically it tells the UI, oh, I tried to run your instruction, but it was going to block, and and because you're the UI, you don't want to block, so I didn't block. There may be actually a way around that now that I think about it, so maybe in another video. I don't know what buttons I'm pressing. We'll go back to the day, But anyway, so we create the channel, we track the first one. If you remember, for part 2, we're creating a feedback loop. So we need to track the first so we can attach it to the end, the 5th one, right? But then basically for each of the values in the permutation, we send its phase setting, and then if it's the first one, we send a 0 to kick off the process. And then we create our new channels, right? Remember, we're linking the output of one to the input of another, so we kind of have this like 2-channel thing that we're chaining. I won't go over this code again, but essentially you're just saying, oh, if I'm the last channel, I actually want to use the first sender as opposed to, the new sender that I just made. But otherwise, what do I do? Well, I call Tokio spawn, right? So for each of the processes, I'm going to create a new task, right? And I just call, I create the process, I call run and await, and then as I'm done, or as I'm, if I'm the first one and I've finished running, I know that my next receive is going to be the last receive, but it will also be the solution for this permutation, right? So I do that. But you can see all of this is happening in a Tokio spawn. So what happens is if we go here, and again, this thread or this process 0, it's waiting for input, right? Tokio knows it's waiting for input, and so it doesn't like schedule it in the task. However, 1 is ready for read, right? If we scroll down here, it's ready to read something. So Tokio will pick it up and do its processing and eventually spit it out to the next one. But the idea is all of these that are empty, they're not just like sitting there taking up a thread and doing nothing, right? Tokio is smart enough to say, oh, these other processes are blocking on receive, and so I'm not going to schedule them to do any work. I'm going to wait for them to get done, right? And as long as something eventually comes around and puts a message on that channel, Tokio will then be able to pick it up, right? Just to like further clarify this again, imagine we have these users and all of these threads. Maybe we have a bunch of these, right? I'm just going to copy and paste really quick. We have a whole bunch of these. Tokio is smart enough to start putting things on the thread, and as things get done, taking them off and putting them back on. And so like when this particular process says, hey, I need to receive on a channel, and that channel doesn't have anything in its buffer, Tokio will throw it off the thread and put something else on that's ready to process, right? And all of these will do their processing, and eventually, maybe all of them are waiting and there's some empty threads, right? These are all just hopefully reiterating the point that Tokio's doing that job that we used to have to figure this out all of ourselves, right? Calling epoll wait, looking for all the events, going through all the events, and putting them in a thread pool that would go process them and stuff like that, right? And it was really cool. I remember I felt I was young and excited being able to do this stuff, but we can leverage something like Tokio to do that for us, and we can get the huge performance gains and better utilization of resources. We just have to know, again, how to use Tokio and how to do its thing, right? And again, because Tokio is really good at it, we just spawn and let it handle its processes. Obviously, we have to be somewhat cognizant. We can't spawn a whole, more than there's sufficient memory to handle. But for example, for part 2, for each permutation I create, I actually spawn a process for that permutation, right? So I don't remember how many, what were there. There's 5 different settings. So there's like, is it 5? There's 5 different ones. So 5 factorial. There's, what is that, 120 or something like that? I don't remember. Should we look it up? We're doing it live. 120, right? So I'm able to very easily just spawn 120 tasks, and then each of those tasks are spawning 5 of their own, right? So now I have 120 plus 600 and what is that? 100, 500, 6 plus another 600 more, right? So now I have 720 spawned tasks, and Tokio's easily able to process them, right? Like if I run this, it happens really fast, right? Tokio is able to handle them all and handle them fast. Admittedly, they're not doing a lot, and they're most of them are spending their time waiting, and so it's really easy for Tokio to pick which ones to do and whatnot. But again, I think it's really cool that we can just say Tokio spawn, and suddenly we do asynchronous stuff. Okay, one last part. Let's talk about the UI really quick, and we'll be done, right? The TUI itself, again, I said often you don't want your UI to like block ever, and that's definitely true. So I did it asynchronously, but there is a potential if you really wanted and it was really important. Like again, if you're doing some kind of graphics programming or game programming, you may not want to use like a quote unquote event handler. But that's what I did here, just to illustrate how you could still run a relatively performant application using something like Tokio and asynchronous programming. But I should say the reason why it works is our cross-term backend. So cross-term is what's doing the terminal work underneath the hood. It allows you to make asynchronous calls. But let's just look at how the TUI works. I won't go over the app and the actual the TUI thing to draw it. You can look at that code. Essentially, the app is just tracking state, and the TUI is tracking. Handling the draw routines. I'm gonna take a drink really quick. Sorry, it's handling those draw routines. Setting up and managing the terminal and stuff like that, right? It's our event handler that handles the events, like imagine a keyboard or a mouse event. And because cross-term can do it asynchronously, we can create an event handler and cross-term can notify us when events are ready in an asynchronous fashion. And then we can do like a little ticker is what we do. I'll show you. But we can say, well, regardless of whether we have an event, we definitely want to fire an event every 16 milliseconds. So I think that's like, I don't remember what the number is, but that gives you like 60 or 100 FPS or something like that, right? And then, so just in our loop, we say, hey, draw the frame, check for the next event, and it will always trigger every 16 milliseconds. So we know we definitely get an event every 16 milliseconds. Then we just handle that event and we do it in that loop, right? So if an event comes, obviously like a key press or a mouse event, we can definitely handle that and redraw. Otherwise, we'll tick and process it, right? So let's just go to this event handler and I'll show you what it looks like under the code, because this uses another feature of Tokio, which is the select method. And if you're coming from Go, you'll be familiar with it. But the idea is if you have multiple channels or multiple things that could that produce futures that could await in Rust parlance, you might want to select on all of those. You might say, hey, just give for this Tokio task, I want you to tell me the first one that's ready, and I'm going to iteratively process them. And that's what works here. And the reason why you want to do this, again, is because maybe you don't get an event, right? So here's the event stream that we're getting from cross-term. And we want to read those events, right? But again, if the user isn't doing anything, in this case, it doesn't matter because our UI doesn't change if the user doesn't do anything. But imagine you're in a game or you're doing you want something to be reactive, like receiving. Maybe you don't send messages, but you receive them. You still want that to show up in the UI, right? And so what we do is, because this may block for a long time, we create a little ticker. And again, its tick rate is set to that milliseconds, so every 16 milliseconds. And then we select on both of them, much like we would in Go's select thing, right? As we say, hey, whichever one of these happen first, process it. Either the tick occurs and we send a tick event, or we get a keyboard or a mouse event from cross-term and we process it. And this is a great way, again, where maybe you have multiple channels, multiple receivers. You want to be able to like work with all of those events in like kind of an asynchronous fashion. You can use this Tokio select method to do that. And again, Tokio has some great documentation on how to do this, right? But the idea being is, you know, maybe not all, maybe you want to like, I don't know, fan in some solutions, or you want to receive events from multiple places. Using Tokio select will kind of help you do that, right? And so that's what I do here. And so again, the idea is if there's an event, go ahead and send it to my, you know, send a message saying, oh, I got a key event or a mouse event, and process it. And that processing doesn't look much different, other than obviously it has to be asynchronous because we're doing it asynchronously now. But if I don't receive an event, I still want to tick and redraw the frame, right? So that's what I'm doing there. Okay, that was a lot of talking. Let's go back to the day. Again, I feel like I did do a bit of refactoring, but I do feel like the async await function doesn't look much weirder than the threading. It feels a little bit cleaner, and part of that again is because I did some refactoring to make it look cleaner. But I actually like the asynchronous programming. I don't have a problem with it. I think it works really well. I will just again say, make sure you're using it where it should be used and not where it should not be used. Tokio is really good about this. There's a I want to give this person credit because they're really good about now I won't be able to find them. Oh man, I will try and find their name because they did some. I think they're on the Tokio team. I'm gonna keep finding. I'm gonna keep working. Oh man. Look at these weird things that I search in the Rust library, right? Oh, I'm gonna feel so bad if I don't find this person. Alice. Here it is. Alice Ryle. They're a great person, and they've done some really cool work. Obviously with Tokio, but they have a blog. I'll try and find it and I'll link it. Sorry, that was a 1 minute or 2 minute like just off the beaten path looking for that person's name, but they've done a lot of work, at least from what I can tell, in answer. Whenever I would Google a question in Tokio, invariably Alice is the person who responded with a solution. So I don't know how active they are anymore or what they're doing right now, but I know at the time, when many of these were done, they did a lot of great work, right? And so kudos to them, and they definitely helped me. But they mentioned some. So why did I bring this all up? Tokio is not meant to be used for everything. Again, if you have something that you need to be very performant and you need is heavily CPU intensive, using something like Rayon, which we've talked about before, right, is better than Tokio. Why? Because CPU bound things don't help Tokio, right? The Go runtime can actually preempt your code. It can say, you've been running long enough. I'm going to pause you and let someone else run. Tokio can't do that, at least right now, as far as I'm aware. So if you like have heavily CPU bound tasks that you want to like run in parallel, spawning a bunch of Tokio tasks is not the right way to do it. You should use something like Rayon, where you can like do them all in parallel and do that processing, right? Anyway, they do a good job of explaining when Tokio may not be a good solution and when it might. And I guess what I would say is most modern languages, or most modern libraries or crates that use that need to do some kind of network stuff will use Tokio, or at the very least asynchronous programming, so you can you can use Tokio if you need to. For example, like MongoDB's Rust driver, it will use is it not actually going to give me? Yeah, here you go. You can see it's using await all over the place. And why is that useful? Well, if you send a call to MongoDB and it's not ready to receive, and it's going to take, some number of milliseconds, let your application do other stuff while you await for it, right? And if you need to block, you can block, right? So there's definitely ways to block, but being able to do it asynchronously is cool. So all of this is to say, and I will once again for the third time conclude my thing, is I think asynchronous programming is cool. If you're using Rust and you're using it for more than just the very basics of Rust, you will almost certainly see Tokio and asynchronous programming, right? If you're ever connecting to MongoDB or a database or doing networking, many of the modern ones will do asynchronous. They have options for you to do synchronous programming if you need to, but many of them will be asynchronous. And what your job is to look in your application and determine where you should be asynchronous and where you should not be asynchronous, and kind of keep them separate. Like, for example, I spent a lot of time trying to figure out a good way for the app and the draw phases to be able to interact with each other, right? So the app obviously has to be asynchronous because it's going to be receiving updates on state, but the draw should not, right? Anytime you call draw, it should just draw, and it shouldn't have to wait for anything, right? So notice the draw does not await, right? I will get there. Especially this draw function right here. Originally, I was like, oh, I can just call render.await here. That's not going to work, right? Because this draw is inherently synchronous. Now, you could call block on to block on this thing doing its thing, right? And that would work. But it was a good reminder to me of thinking about where you should be using asynchronous programming and where you should not, and making those delineations. And it's the same thing in other languages, right? In your Go code, you're going to have places where, it's good to fire off a Go routine because you're going to be doing some amount of processing, and you don't want that to affect, some other thread that's doing processing, right? And so, but even in Go, I've seen people just use Go routines for literally everything, and it's not actually helping you out in the end, right? And so I think that's what's cool about Tokio, is they're very upfront about it and say, hey, here's the places where it's useful, and here's the places where it's not, right? And again, so I'll link this tutorial. It's a great thing to go through, especially think about the spawning right here. They go through a little mini Redis example that I think is really useful, right? So if my code isn't making sense, and I wouldn't be surprised if it doesn't, obviously let me know what I can do to improve, but you can also look here and kind of walk through this tutorial to see how it works. And they handle topics like binding with sync code, right? Like I was talking about, there may be places when you want to do that, right? They talk about, hey, how can I do selecting on different things? How can I do channels, which is what I was using, right? So there's a difference between channels in Tokio and the ones you might use in the standard library, right? So just things to think about as you're doing that stuff. So there you go. There's day 7 out of the way. I think I've refined it enough that I feel comfortable with day 7 being done. So I think my next video will be the new, whatever the next excuse me, whatever the next day is. I don't know what it will be. I apologize for the hiccups, and we'll talk to y'all next time.